Hey guys, Mr. Mises here, and I want to talk to you today. No bells and whistles on this one. I just want to give you a straight up video here on linear regression, and this is a basic introduction of linear regression, including the formulas that we use. None of this will be really in context, but later on, another video, or when we get doing this in class, we definitely want to do this stuff in context. So I've got a scatter plot here. And it's just a a scatter plot with a few numbers here, and again I have no context here. We're going to say this of course this is our x-axis, right? So this is our x variable, and this is our y variable here. If I was to draw a line, okay, like you learned in a long time ago, middle school or whatever, that you can draw a line of best fit, and it would look something like this somewhere. Right, somewhere around there. Well, we talked about this is the best fit line. Well, what is the best fit line? Really, what are we trying to do when we're making this line of best fit? Is it trying to get the most points in here? Is it trying to make the differences be close to one another? Well, in statistics, we often call this line the linear regression, or the line of regression, or the least squares line. And let me tell you where we get that term from. Notice here that in this line we can make from our point to our line, we've got a bunch of differences, right? We've got all these differences. And if I make a little square here out of these differences, okay, this is called the squared residual. This little difference here, this difference is called a residual. So the residual is the difference from the actual and the predicted value that we would get on our line. Now I'm going to talk about that real quick when we get there, but we want to find this equation of the line. Now, to find that equation of the line, we really got to think about what are we trying to find here in terms of these differences. And if you think about the line as being kind of the average, then we're talking about taking this line and moving this line so that, let's see if I can get the line, moving this line around so that the average distance, these areas, are going to be minimized. So we want the minimum area of these squares as possible. We want them to be as small as possible, so that way the smaller they get, the closer our values to that line, the better our predictive analysis is. The closer we're going to get to predicting to the actual. So if you remember what average distance to something is, we called that standard deviation. So in essence, the slope of this line can be kind of related to the rise and run of the standard deviation, the ratio of the standard deviations of y and x. In fact, it turns out that the slope of this line, and we call this in statistics, we use b with a subscript of 1, so that's the slope. That's the slope of regression. The slope can be calculated by taking our correlation coefficient, which tells us the correlation between the value between x and y, how closely related these points are to that line, times the ratio of the standard deviations. And hopefully that makes sense. Our slope is how the ratio changes of these standard deviations, these kind of differences. So that's a way we can find our slope of that line. Now, we're not done totally yet, because let me write on the side here, what we're really looking for is we're looking for the equation. The equation of this line is written as y hat equals b sub 0 plus b sub 1 times x. B sub 1 we just said, right? B sub 1 is the slope of the regression. What do you think b sub 0 is? B sub 0 is the y-intercept. So how are we going to find the y-intercept? Well, it turns out that if we think about this line as being kind of the average. We're regressing towards the mean. We're getting closer and closer to the averages of the two. Then this line can be relate these two averages. Y bar, the average of the y's, is going to be equal to the b's of 0 plus the slope times the mean of x, right? This would be the average. Averages related to the average, okay? So what we can do is we can solve for b sub 0, and we can get b sub 0 equals y bar minus b sub 1 x bar. So what we're saying here is that we can find the y-intercept by taking the mean of the y variable, subtract it from our slope, which we found earlier, times the mean of the x variable. Now, so basically what I'm saying here, guys, too, is if we have the summary statistics of our y and we have the summary statistics for our x, don't forget this is a quantitative variable, right? Y is a quantitative variable, x is a quantitative variable. So if we have the mean of the y's, the mean of the x's, all the summary statistics that we need, including the standard deviations and r, then we can find out the equation of our linear regression. Now you can see here that we're talking about means and standard deviations. So you're probably thinking to yourself, at least I hope you're thinking to yourself, that we would like x to be symmetric and we would like y to be symmetric. Well, what happens if these are not? One of these two is maybe skewed to the left. Well, if one of these was skewed to the left, we might see some curvature in our data. So in our data, when we see that curvature, it might be a curve and we might not be able to do a linear regression. It might not be appropriate. So what I want to do is I want to use these two formulas to show you how we would calculate and determine this regression equation using some summary statistics. Okay, so let me go on to an example. So here we got two examples. I've got some summary statistics. I got x bar, y bar, the standard deviation of x, standard deviation of y, and my correlation coefficient. So I'm going to use my formulas. The first one is b1 equals r sy over sx. Okay, so b1 is going to be 0.85 times 4.2 over 1.3. Throw that in the calculator and I'm going to get about 2.75. Then I'm going to calculate b sub 0 using my other formula, which was y bar minus b1 x bar. Alright, so I'm going to get y bar is 122, b1 is what I just got, 2.75. Okay, I got that from here. Times x bar, which was 35. And I calculate all that out and I get 25.75. So then when I put it all together, I'm going to get y hat, that's what we call it, y hat, it's got a little hat on, y hat equals b sub 0 plus b sub 1 times x. So y hat equals b sub 0, which is 2.75, plus b1, 25.75 times x. And that will be our linear regression. Now, later on when we start doing this in context, I'm going to have you write these variables in context, y and x. But for now, I just want to get you to compute these the correct way using the formula. All right, so why don't you try example number 2. I'll take a second for you to pause it and try it out. Okay, so b1 is going to be r times sy over sx, which is going to be negative 0.196, and b sub 0 is going to be y. It's going to be 65 minus negative 0.196. Again, I got that from here, times 225. And that's going to give me a y-intercept of 109.1, And so my formula for regression is y hat equals 109.1 minus 0.196x. And that is how we find our line of regression, least squares line. Sometimes it's called LSR, least squares regression, by using our formula that we got from looking at the standard deviation and the means. All right, okay, catch you soon. Bye. Catch you soon. Bye-bye.